All right, section 3.1.3, solving linear inequalities. So today we are going to start looking at stuff that do not equal, right? So the things that do not equal. We'll talk about the different types and what to do with them. But they are so very closely related to equalities, equal signs. This shouldn't be a long section at all. Alrighty. So you've got some properties listed down here. You'll notice some things. But essentially, you've got 5 different inequality signs. There's less than, greater than, less than or equal to, greater than or equal to. Okay? So this is less than, greater than, less than or equal to, greater than or equal to. Alrighty. Now with these, obviously, there's a lot more that is less than. So when you've got stuff like 2 equals 2, there's only one thing, there's only one solution there, right? 2 only equals 2. But there are a lot of things that are less than, or 2 is less than. So like 3, 4, 5, 6, 7, 8. A million, so on and so forth. As long as you keep the inequality sign, you don't need to list them out, right? You can just say that x is greater than 2, or 2 is less than x. But notice, as I mentioned before in an earlier video, that is going to affect the symmetric property, right? So it's going to affect the symmetric property. 2, in fact, let's just erase this real fast. 2 is, so x equals 2 is definitely the same thing as 2 equals x, right? Definitely the same. However, 2 less than 3 is not the same thing as 3 is less than 2, right? Because one of those is a true statement, the other one is not. 2 is less than 3, but 3 is not less than 2, so you cannot use the symmetric property the same way. If you're going to use the symmetric property, 2 less than 3 would be the same thing as 3 greater than 2. You are welcome to switch them, but you also have to switch the sign. All right, so that's very important note when it comes to symmetric property. Okay. Now from that property, it changes one of our solving rules as well. Because of that fact, because when you switch it, you change it around. When you multiply or divide by a negative number, it has an effect on that sign. It also switches it around. And it's not just because you want to avoid this situation, it actually changes it. And it comes from the fact that a negative times a negative is a positive, right? And because the sign changes, the inequality sign will change as well. So what these rules state, the first 8 of them, are basically saying that, the first 4 of them are basically saying the same thing. You can do everything, all the properties of equality still apply, as they do with equations, right? But when you get to the property of multiplication property of equality, and the division property of equality, if you are multiplying by a negative, then you must switch the sign. If you are dividing by a negative, then you must switch the sign. That is not for every single multiplication. It is not for every single division. It is only for those that are negative numbers. So let's take a look at that. So we've got this standard, inequality here. We know that 2x plus 4 is less than or equal to 10 plus 5x. Solving along, you get down to here. Negative 3x is less than or equal to 6. When you divide by negative 3, both of the sides still follow the same rule. Right? So these will cancel. You're left with x, right? 6 divided by negative 3, pardon me, that's a typo, a negative 2. But notice what happened to the inequality sign. No longer is x less than or equal to negative 2. X is greater than or equal to negative 2. Because these two multiplied together give you a positive, you had to flip the sign. Okay? That's the only other thing. Other than that, solving inequalities is exactly the same as solving equalities. Just watch out for that extra step. It's not guaranteed it'll happen. You don't have to do it every single time. You don't have to go searching for it. But it's just an extra little step that sometimes you may have to deal with because of that fact that negative times negative is positive. Alright, so let's go jump on down. Again, you've got some steps to following inequalities, but they're so similar to the equality ones, I'm not going to waste time going over that. Okay? Excuse me. Solve the inequality. Negative 3x minus 4, all of it divided by 7, is greater than negative 5. All right, we could make a chart. We could definitely make a chart, make a table. You will definitely have to do that on your test. But for inequalities, since we've gotten so used to that, let's just go ahead and solve it. So let's put it down here. Negative 3x minus 4 divided by 7 greater than negative 5. Alrighty. I'm going to go ahead and pretend that says equal instead of greater than. I'm going to pretend that says equal. If that said equal, the first thing I would do would be what? What would be the first thing I do? I want to start as far away from the variable as I can. So first I check that the x is on one side. It is. Good. And now I want to start with the thing that's the farthest away from the variable, which in this case would probably be the 7, right? So I've got this divided by 7. I'm going to cancel it out with a multiply by 7. When I do that to this side, the only thing that happens is the 7's cancel. I'm left with negative 3x minus 4. What I do to one side, I must do to the other. Again, I'm treating this exactly like it said equal, right? I end up with negative 35. Now, I multiplied, but did I multiply by a negative number? No, I did not. So this would still be, hang on, so minus 35. This would still be greater than. Cool. Moving right along, I'm going to, again, treat this like it said equal. The next thing I would do is get rid of the 4, add 4 to both sides. Do that up here. I'm left with negative 3x on one side, right? So add 4, that goes away. Add 4 over here. Negative 35 plus 4, though, is going to be negative 31. Yeah, okay. And I was adding, so it still stays the same, right? All right. Lastly, again, if it was an equal sign, I'd divide by negative 3, so I'm going to divide by negative 3. And I'm just going to keep it as a fraction, totally fine. I get x on this side. I get, okay, negative over a negative is going to be a positive, so I get a positive 31 over 3. But this time, I divided, and it was by a negative number. I divided by a negative number, which is a problem. So it's going to be less than, not greater than this time. So I switched the sign. From here to here, I switched it around. And I get x is less than 31 over 3. Notice it was the exact same thing except for that last step where I had to switch the sign. Alright, let's try another one. Solve the inequality. 5x plus 4 is greater than or equal to 11 minus 2x. Alright, let's try this one out. So I'm going to do it the same way. 5x plus 4 is greater than or equal to 11 minus 2x. 5x plus 4 is greater than or equal to 11 minus 2x. I have an issue here because there are variables on both sides, right? So I want to get rid of that first. In the last problem, x was conveniently on one side for me. So now, not quite the case here. I think what I'm going to do is try and put it on the left. Again, I could put it on the right, totally legal. I'm going to try and put it on the left though. So add 2x to both sides. I end up with no more x's on this side. 7x plus 4 is greater than or equal to 11. It's a hideous color. Hold on one second. 7x plus 4 is greater than or equal to 11. Alright, x is conveniently on one side now. Now I will start moving things away from it as far away as I can. Minus, let's use blue, minus 4, minus 4. And I've so far added and subtracted, so I'm not worried about that inequality sign, right? I'm not worried about that yet. So far I'm adding and subtracting. I'll go up here now. I'm left with 7x greater than or equal to, what, 7? 11 minus 4? Yeah, 7. Last but not least, I'm still treating it like it's equal. Divide by 7. I get x and 1, right? 1. 7 divided by 7 is 1. And since I divided, but it was not by a negative, so the sign remains the same. X is greater than or equal to 1 is my solution. Alrighty. Hopefully you're noticing all these parallels between equalities and inequalities, and the only time that's different is when you divide or multiply by a negative number. So I'm going to let you guys try this last area out, this inequality out. Go ahead and pause the video, try it out. Remember, if you don't do it yourself, you are the one who's going to be failing the test, and I will not cry for you. So make sure you try it out. Doesn't matter if you get it wrong right now. It matters if it matters if you get it wrong on the test. So pause the video, try it out. I'll see you back in a few minutes. Okay. I hope you had a chance to try this one out on your own. Solve the inequality 6x plus 4 is less than or equal to 5 plus 8x. So I've got 6x plus 4 less than or equal to 5 plus 8x. Alrighty. I have variables on both sides, which is an issue for me. I normally go from left to right. I'm going to keep doing that. Maybe you went from, I normally put things on the left from the right, and maybe you did it that way, like I'm going to, but maybe you want to go the other way. Maybe you want to subtract the 6x. I'm actually going to subtract the 8x. Why? Because life is cool like that. And America's cool like that. I get to free to choose what I want to do. So negative 2 plus 4 is less than or equal to 5. Sweet. Cool. Now, I will move the 4 part over. Oh, wow. Okay. I'll move the 4 over. And I end up with negative 2x is less than or equal to 1. And then I'll divide by negative 2. I get x is less than or equal to negative 1/2. Awesome. Okay, what did I just do wrong? Talk about it. I did something incorrect. What did I do? It was not switching to both sides. It's the sign, the inequality sign. That's a problem, right? What did I do in this last pink step? I divided by a negative number. So I don't want to keep the sign I have. That's wrong. I want to make it positive. I want to make it greater than. X is greater than negative 1/2, right? So you got to watch out for that last step. Alrighty. Now a word problem. Always everyone's favorite time. So you may be thinking, okay, cool, but what's the point, right? So let's check out this word problem. We'll see if we can actually solve it. Remember, we're going to translate, solve, translate back, right? That's always how we solve a word problem. In 2008, about 66.1 million U.S. households had both a landline phone and a cell phone. At the time, it was expected the number of households with both landline and cell phone would decrease by an average of 5 million households per year. Approximately 28.8 million households had only cell phones, and it was expected that this number of households with only cell phones would increase by an average of 15 million households per year. According to this data, about how many years would the number of households with only cell phones be greater than the number of households with both cell phones and landlines? Alright, that's a lot of information, right? That's a lot of information. So let's start by just underlining, right? Because that's a great skill when you're given a lot of information like this. Let's start with just underlining, because they talk about 2 different types of households, talk about years, now they want us to compare the 2, like there's a whole mess of crap going on here. So let's just start with this first sentence. In 2008, that doesn't sound very important, so I'm not going to underline it. About 66.1 million households, I think that sounds pretty important, had both landlines and cell phones. 66.1 million had both. I could even go so far as to write that down here. 66.1 mil had both, right? Then they said something else. At that time, it was expected that the number of households with both would decrease by an average of 5 million per year. Interesting. So that number would decrease 5 per year. Alright, so it looks like that's the information about both. Right, that's the information about both. Very similar thing going on here with the number of cell phones, or the number of households that had only cell phones. Approximately 2.78 million had only cell, right? Had 2.78 million had only cell, so let's write that down. 27.8, did I say 2.78? My apologies. 27.8 million had only cell. And it was expected that this number of households with only cell would increase by an average of 15 per year. 15 per year. So increase an average of 15 per year. And then that looks like all the information for the only cell. Okay, so that's much more easy to do with 4 lines of information than all this stuff, right? There was a lot of words there we didn't need to know. So underlining, translating, that's a really important skill to have. Excuse me. Okay, the last thing I want to know is the question. According to this data, about how many years would the number with only cell be greater than the number with both? So in how many years would cell be greater than both? That's the question, right? That's the question. Alright, cool. Now, when I set this up, my translating, remember when I translate this English into math, I want to set up some sort of x involving equation. So in order for me to do that, we need to actually think about what we want x to be, right? Because we need x to actually represent something. Last time it said what is the number, right? So x was the number, right? This time, what would be the answer to our question? Let's say we solve this and I get the answer of x equals 2. What does that mean? Well, then that means it would take 2 years for cell to be greater than both, right? And translate it back. So in other words, x is going to represent the years, whatever those years end up being. It's going to represent how many years until cell is greater than both, right? So x represents how many years. And I notice the year also happens a lot up here. So that's good. I can make expressions out of these that involve x because it's per year, right? Alrighty. If you have any questions on that part, make sure you pause the video now because that's going to be the entire next chapter. So I want to make sure you guys this is an introduction to the next chapter as well. So I want you to make sure this is starting to make sense. Alrighty. The next step is to make expressions out of both of these. Remember, expressions don't involve equal signs. That way we can put them together as they have asked, right? So we want an expression for cell and an expression for both. So let's try that, the both expression. Let's see. I start with 66.1 million, and then what's going to happen? It's going to decrease 5 per year. Well, if I directly translate that, that's subtract 5 per year was our x's, so subtract 5, per year. 66.1 minus 5x. I have my expression, okay? I want you to take 30 seconds now. You don't even need to pause the video. I'll just give it to you. Come up with the same kind of expression for cell phones. So only cell. You guys come up with the same kind of expression for only cell. Okay, that really is all the time it should have taken. If it took you longer, then you need to make sure you maybe pay more attention and just know that you are going to need to get some help, okay? Anyways, so I've got 27 to start with. Let's do it in red because it's about cell, right? 27.8 to start with. Increasing means to add. 15 per year is the x's. So plus 15x. That's my expression. Sweet. Now, I have to be careful when I set this up in the equation, in the inequality, right? So let's take a look at the question one more time. How many years until cell is greater than both? Well, cell was red. So how many years until cell greater than both? And we don't want equal to because we don't care about equal to. We want greater than, right? All right, so let's go set that up over here. Cell was red, so the 27.8 plus 15x, right? That's the expression for only cell. And we want greater than our both, which was in green, 66.1 minus 5x. And we have our inequality. We have successfully translated. Notice that when we underline and we define things, it gets so much easier to do that, right? So much easier to go from a huge paragraph of information into a nice little equation. That's the whole point of this, to be able to take huge, ugly things and make them into math so we can actually solve it. We can answer the question. So let's go ahead and do that part now. Let's solve it. Alrighty, I'm gonna move this green x over to the other side, so I'll add 5x to both sides. End up with 27.8 plus 20x is greater than 66.1. Addition does not require me to switch anything, so I don't have to worry about that. Subtract the 27, because now that x is on one side, I move as far away from the variable as I can. So subtract 27.8. You get 20x is greater than 38.3. Divide by 20. And you end up with x is greater than, or x and 1.159. Now I divided, so I have to be careful. Do I need to switch it? No, because 20 was positive, right? So it would stay the same. So x is greater than 1.915, which is fabulous, right? We can solve things. But what does it mean? So far we've translated, we've solved. Now we need to actually translate back. We need to answer that question. So the last thing is, if x was years and x is now greater than 1.195, then that means it will take over 1.915 years for cell to be greater than both. Okay, and that would be our final answer. You probably could round that to 2. It'd say over 2 years for cell to be greater than both because it's so close to 2. But if you wanted to be super accurate, you'd say over 1.915 years. So at 1.916, they will be greater, right? And you can say that with certainty. And we've solved our equation. Alrighty. So today we've talked about inequalities, how they're virtually exactly the same. So far we've talked about it. And we've talked about translating, right? Next up we're going to solve exponential expressions in just a minute. But if you have any questions at all between now and the next video, you need to get them answered. Okay, you need to answer your questions, and I will see you in the next video.